Okay, hello everyone. Thanks for joining our track on Maple and mathematics this afternoon. We are happy to have a few presenters. We won't be able to fill the full hour because some didn't show up. Perhaps they will join us later on so we can rearrange the order of talks. My name is Thomas Richard. I'm an application engineer in the German branch office of MapleSoft, and I'm happy to moderate this afternoon session. Each speaker has 10 minutes, which is a strict limit, and allowing for 5 minutes of questions and answers afterwards. If you have any questions on those contents presented, please type them into the Q&A panel, and I will read them aloud after the presentation. There will be enough time left. After the last presentation is over, we will still have some time for the full stage. Everybody can share their questions and possibly answers, and we're hoping for a good discussion. And when the session is over, I will say a few closing words. Okay, we'll start out of the scheduled order. We'll start with Oleg Antoniuk. And I was originally wanted to say that we have a strong Russian appearance and attendance today, but since those two speakers haven't yet made it, we'll start with Oleg, and I think from his name I can infer he's also Russian, perhaps, but nevertheless,
well, in fact, Ukrainian.
Okay, yeah, almost. Wonderful. Okay, Oleg will present an algorithm to derive a rational function that passes through chosen points based on expressions for divided differences.
Okay, Oleg, thank you very much. Thank you very much for the announcement. I will share my screen in a moment. Yeah. Due to shortage of time, I'll try to go a bit quicker through the presentation. Okay, so a conventional way to derive a rational function that passes through a number of given points would be to solve a set of linear equations with respect to coefficients BL and CG. Yeah, and in that way we could get the right coefficients so that this function will pass through P points, and and that would be it. But in this presentation we will solve this problem in a different way, just for the fun of it, but also maybe for a potentially faster algorithm. Yeah, so let's start from the very simple case, a rational function of the order n0, the numerator of the order of n and denominator of the order of 0, which is actually a polynomial. And for that, there is a Newton interpolation formula that gives an expression which depends on a value of independent variable and a number of coefficients. And those coefficients make sure that it takes value omega1 at z1, omega2 and z2, and so on. Yeah. However, in this presentation, I will use a little bit different definition of a divided difference than usually seen in the literature. This is given by the function delta, depending on two indices, which recursively calls itself as given by the expression. I will call the first index the order of a divided difference, and the second is simply a supplementary index. Yeah? But those differences are exactly the same to those ones that are often given in the literature, as illustrated at the bottom in the equation. For example, delta 2,3 is equal to omega1, omega2, omega3 in the brackets. So basically, expression on the left is equal to expression on the right, although it's written differently. We can simplify it to 0 in Maple. So those are the same values of divided differences. Yeah. So to make a transition from a polynomial to a rational function, we could have a look on another specific simple case, which is a rational function of the order 1, 1. So just a linear function divided by linear function. And when it passes through 3 points, it can be written down as given by this equation. Yeah, and if we look at those objects which are highlighted with ellipses, those are really similar to divided differences. However, they are defined as sort of in upside down way. So difference between values of z divided by divided differences. Yeah? And apparently, it's possible to generalize this approach into a longer so-called continuous fraction or staircase fraction. Yeah, that takes also p-values, takes p-values of omega at p-values of independent variable, and it can be written in a way like this. Apparently, it's also known in the literature, as I found it in one of the books, reference 1. However, again, there was a different definition of the divided difference. But here I will stick to this definition, which is given by delta NM, which is similar to the definition from the previous slide, but just upside down. Yeah? Okay, but when we convert this rational function to a canonical form, we will end up with, of course, it will take p-values at prescribed values of the argument, and the denominator, the order of the denominator will be equal to the order of the numerator, or maybe there will be a difference by 1. Yeah. So when we grow this staircase equation, then when it gets step by step larger, that in one step it gets numerator order increased, and in the other step denominator order increased. So we don't really have a control here over the n and m of the orders of the polynomials. So they will be either equal, or denominator will be, or the numerator will be having an order which is by 1 larger than denominator. Yeah. And how to address a more general case, we will have to stitch those two equations together somehow, Newton polynomial and continued fraction. Yeah? So something like this. Yeah? So we will start as a Newton polynomial for a number of steps, and then we will stitch the continued fraction to it at the end. Yeah? And this parameter k will be defining either it will be a polynomial, or it will be a polynomial with extra or it will be a certain rational function. So the equation will look like this then. Yeah. So it starts as a Newton polynomial, and at the end, instead of finishing it at delta k plus 1, we just add a continued fraction tail which goes down and down. Yeah? And then the definition for the divided differences will be quite simple. The same as before in the previous slides. Delta 0k is simply the value of omega that function should take at z equals ek. And for higher orders of the for higher orders of divided difference, it will be defined as a recursive function the m minus the n over the divided differences. And for small orders of divided difference, it will be like upside down. Okay, so this is already complex enough. Let's program it in Maple and see what happens there. So this is a worksheet that I created to demonstrate it. So now I just run a definition, which exactly as stated in the slide. For the first index equal to 0, it takes omega value omega. And then for large values of the large orders of the divided difference, it's z1 minus z2 divided by the differences. And for the small values, it's other way around. So what happens when we try to run it? Then this function dg recursively calls itself, and then it expands the expression into something like this. Yeah. And again, we don't have to stop here at dg 3,4. We could continue as a continued fraction, d 3,4, 4,5, 5,6, and so on. And when we expand those into a final expression, it will be something very big like this. But we can take this expression and do analytical verification that it does what it should do. So at z equal to z1, it takes omega1, z equal to z2, it takes omega2, and so on up to z6. And yeah, so apparently it works. And this is a case where k is equal to 3, for which we end up with a rational function of the order 4(1). We could also test analytically the other case where k is equal to 1, and then it will be a rational function which has the order of 3(2), and it also does the same thing. At z equal to z1, it gives omega1, and so on up to omega6. Yeah. So apparently it works. So it gives. So it has order of n in the numerator, order of m in the denominator, and it takes values, prescribed values of the omega at values z1, z2, z3, and so on. Yeah. So we could actually also check if this polynomial, if this function has correct order of the numerator and denominator. We could just substitute certain values, and that was not right because I didn't run this before. Okay. Yeah. So apparently this is what happens when we substitute a number of values and we simplify it, and we see that it's really a rational function of the order 4(1). Or we can do the same trick with another case, and k is equal to 1, and the staircase structure, the continued fraction, is starting right away. And then it has.
May I remind you of the 10-minute limit? Please.
Yeah.
Try to come to an end.
I'm so sorry for that. And then we simplify it, and we actually end up with a rational function of the order 3(2). Yeah. So apparently it works, and if we have k equal to 5, that means Newton polynomial extends until the end of the formula. We have 5, 0, which is a polynomial. When the staircase function, the continued fraction starts earlier, for k equals 3, we end up with 4(1), and when k is equal to 1, we end up with 3(2). Yeah. So the only thing I did not figure out yet how to make the order of the numerator less than the order of the denominator. The only possible trick would be just to define inverse functions that takes inverse values, for example. So that would be a way to cover it. And indeed, I just tried these values, and the formula gave me the answers for all those functions: 5, 0, 4, 1, 3, 2, and 2, 3, 1, 4, 0, 5. And they all seem to do what they should do, to take the right values at the right values of the argument. And indeed, as an outlook, we considered so far only this kind of staircase function, which we have k steps of Newton polynomial and then continued fraction. But we could also derive other structures like this or like that. But I have not figured out the formula for divided differences for those yet. Yeah. So at the summary, it's just possible to integrate the Newton polynomial equation as interpolation equation with the continued fraction part and address all kinds of rational functions, not only polynomials. Yeah, and to do this, we have to adapt the definition of divided differences, which depends in a piecewise way on their order. And what would be a useful thing from the point of the algorithm? You could actually, instead of calling a recursive function, you could save those expressions for divided differences and reuse them. So it may be an algorithm to derive the rational function kind of faster than just a solution of general solution of linear equations. Yeah. So I'm sorry for taking too much time, and I thank you for your attention.
Thanks a lot, Oleg. Impressive talk. And due to the exceeded time, we have left time only for 2 questions, I think. One is about your Maple implementation that you have on screen. Is it available for download, or did you upload it to any resources like Application Center or Maple Primes so that others can access it?
Oh yeah, I would like to share it, but I think when I uploaded the files, I did not include it into I did not include it maybe in the zip file that I send around. The zip file here.
It's not necessary to do this right now. We have plenty of time left after the conference. It would just be of interest to many users of Maple to have that available, because your implementation
yes,
seems to be
sorry for that. I really did not include the worksheet into the zip file, but I would like to share it if possible.
Yeah, no worries. There are many approaches. You can use Maple Primes or our Application Center, which is currently in a new beta phase, making it a bit more easy to access. You'll find out which is the best way to do so. Question number 2 is more about the example that you have shown with p equals 6. I think that was on slide 12.
Okay, slide 12, yes. Yeah.
Exactly. You have chosen the argument values to be distributed symmetrically around the origin. We're wondering if that's too special, or is it a special case? Does it affect the generality of results? What about non-uniform distribution of argument values or even random values?
That's a very good observation there. Thank you for that. Indeed, I put the z values symmetrically, but I did not intend to explore only symmetrical case. Due to the analytical verification in the worksheet, we can see that in principle it should work for any values, because I just substitute analytically z1 and simplify it with Maple, and it gives the omega 1 and omega z5 converts in omega 6 and so on. So due to analytical verification that it works for any kind of values, so it should in principle work also for random values of zk. But indeed, for the numerical verification, I used only symmetric case.
Sure, which makes sense here. Okay, thank you. Thanks again, and we'll move on to the next speaker. For those in the audience that have shown up a bit later, let me remind you that we are deviating from the scheduled order, and we'll proceed with Alexandre Trocado. And he's talking on...
I will stop sharing.
Yeah, of course. Thank you. And Alexandre will talk about visualizing the intersection curve of 2 quadrics with Maple, investigating algebraic, geometric, and computational issues.
Okay. Hi, everyone. I want to share. Can you see my screen?
Yes.
Yes, we can.
Okay. Okay, I'm here to present the work done by me and Professor Laureano. The aim of our work was to show how to implement a new algorithm to compute the intersection of 2 quadrics in a more direct and easy way. The idea of our algorithm is to start by determining the projection of the intersection curve into the plane, getting what we call the cut curve, analyzing the topology of this curve, determining the critical and singular points, and finally make the lifting of the cut curve in 2 different ways: through the exact parameterization of the intersection curve, or when it's not possible, using the discretization of this curve. Our work was essentially devoted to the most difficult case, in which both quadrics are defined by two polynomials of the second degree. To compute the cut curve, we use the resultant of two polynomials, f and g, in order to the z variable. This curve is defined in a planar region defined by the discriminant of f and g in order to z variable. The two discriminants define a planar region when the cut curve is inside. The lifting of the cut curve can be done easily using this equation. This equation is obtained by polynomials f and g, f equal to g, and solving this equation in order to z variable. The points when can we use this equation are those where the denominator do not vanish. Points that cannot be lifted by this equation correspond to singular points of the cut curve and are lifted by the equation of one of the quadrics. Other singular points of the cut curve we proved that corresponds to tangential intersection points or singular points of one of the quadrics, and all can be easily lifted by the equation that lifts irregular points. We have implemented in Maple our algorithm with 15 examples with a quite satisfactory results. These examples was obtained from the web page from the authors of an algorithm that actually intersects quadrics, two quadrics. Is a very difficult to implement. So with our work, we wanted to implement an algorithm that simplifies this work. With our algorithm, it was possible to represent the intersection curve between two quadrics topologically correct and showing the points that come from tangential intersection. This is very difficult to do with Maple, and with our algorithm, we could obtain these tangential intersection points. Conclusions. We introduced a new approach to analyze the intersection between two quadrics. New tools were provided for the analysis of the cut curve and computation of critical and singular points in an approach that not intended to classify the intersection curve. This algorithm has been fully implemented in Maple and shows a very good practical result. You can see with more detail our work and our tools in this paper that has been published this year. Thank you.
Thank you, Alexandre. That was a bit quicker, so we have more time for questions. Let's wait for some more. Okay. I've put the URL to the online calculator into the chat panel so that everyone can try it out right now. So expect some overload. Okay. For computing, or for the topological analysis of the cut curve, for instance, for finding singularities, did you implement your own algorithm, or did you, for instance, access Maple's AlcCurves package, which has a singularities routine? What was your access or your approach to that problem?
We did not use any package from Maple. With only mathematical tools direct. We implemented only resultants and and computing zeros of the resultants. Only that, did not use any package from Maple.
Okay, yeah, I'm just wondering. I think the AltCurves package is restricted to planar curves having two independent variables, so that wouldn't have helped you probably. Okay, there's a new question from the audience. Is it possible to extend the algorithm to a general surface?
I don't think so, because the degree of the resultants explode when we increase this method to superior surfaces to 3 or 4 degrees. From 2 degrees, it is possible. 3 or 4 degree surfaces, it will be very, very expensive because the degree of the resultants increases very fast.
Yeah, of course, that's a combinatorial problem, sure. Okay, thank you. There's another question which is related to the recording, to the extended version of your talk. In determining the critical points of the cut curve, you mentioned the discriminant, which is called sigma 0 of x, and you said it has a degree 12, right? Sigma 0, I'm not sure if it's in your slides today.
Yes, not in this slide, but in the video, I told that.
In the video, yeah.
It makes.
Yeah, you mentioned that the discriminant has a degree limit of 12, and that all its factors have a degree limit of 8. And both of these results are not self-evident. So could you elaborate a bit on how you found this?
Okay. We have a theorem that was proved using Maple. Was quite difficult to obtain using Maple. We saw that the degree of sigma 0 was bounded by 12, and any factor of sigma 0, the degree of any factor was less or equal to the degree was less or equal to 8. We just proved this using Maple. Our experimentation in Maple was running like a week to prove that, and Maple did 1 week in a good computer, and finally we obtained these results. It was an experimental result, not a theoretical result, but Maple give us a very good help here to obtain these results.
Impressive. 1 week for a non-trivial result. That's very impressive. Good. There's one more question that came up in the chat panel, not in the QA panel. Jakub Aliev is asking, can you write parametric representation of the intersection curve if it exists?
Can you repeat, please, the question?
Can you write a parametric representation of the intersection curve? Does it exist?
Some cases we can. Some cases. Other cases we cannot. We just went to the discretization of the cut curve, and the lifting of this curve was not easy to do that. Some particular cases it was easy to parameterize the intersection curve, but you have to see the full paper to understand all these details from every case.
Yes, of course. As you said in your title, you have considered both algebraic and geometric as well as computational issues. That's nice. Thank you. So let's come to our next speaker, which is Alexander Gusev of Joint Institute for Nuclear Research in Dubna, Russia. And he is speaking and presenting an algorithm for constructing a Hermite interpolation polynomials on a triangle and on a tetrahedron.
You hear me?
Yes, we can hear you.
Let's start the algorithm to formulate interpolation polynomials Lagrange and Hermite on the in general case in a simplex. This is a part of the scheme of the finite element method where we develop some scheme to solve elliptic partial differential equations in nuclear, molecular, and atomic physics. This is boundary value problem up to 6 dimensions. And for its solving, we construct the Hermite interpolation polynomial. So it's this used if needed high smoothness between the element. So this second advantage is that each node of space will be common to more finite element. So the algorithm based on the algorithm of analytical construction, this one-dimensional Lagrange and Hermite interpolation polynomial and the multidimensional Lagrange interpolation polynomial, which is known in analytical form. For example, two-dimensional case, the Lagrange interpolation polynomial equal to 1 are the product of the equation of the lines presented of this figure. So the problem is construction of the Hermite interpolation polynomial, join which the piecewise function can be obtained that possess continuous derivatives. Basis of the analytical calculation of the one-dimensional interpolation polynomials, we use the some type of the polynomial, auxiliary interpolation polynomial of the first type, which is determined by this equation. So in multidimensional case, this values is not form the basis of interpolation polynomial, and we need two types of interpolation polynomial. Second type, which is needed for continuance of the derivatives, and third types polynomials is needed for construction the basis. So how we construct them? The algorithm is follow. We answer to question how polynomials we have and how polynomials is needed. So it is presented of the example nights or the interpolation polynomials that possess the second derivative, the Hermite basis functions of finite element pair that possess second derivatives is smooth of the second derivatives. So, and next, the same algorithm, but we use the conditions for two-dimensional case of the edges. So, and the same algorithm it is needed for the three-dimensional polynomials of tetrahedron and in simple and of high-dimensional simplex. So, this is some result of the Hermite interpolation polynomials for the two-dimensional, three-dimensional case. Here is the other polynomials and how types of the interpolation polynomials is given. Other case, the interpolation polynomials of the Gipper cube. In this case, the polynomials are given in the product of the one-dimensional case, one-dimensional interpolation Hermite polynomial. This example of the analytical polynomials. So some results, we apply the finite element schemes. Here is present two-dimensional finite elements to solve the Gelbon's problem on a square which have analytic solution. So the discrepancy versus the energy is presented here. We show that the two-dimensional Hermite and Lagrange interpolation polynomials on the square works better, but the Lagrange and Hermite interpolation polynomials on triangle are more universal. The same picture for the third order, for the fifth order. Here is the example of the four-dimensional Gelbon's problem. And this is my resume. Thank you for attention.
Thank you, Alexander. That was also a bit quicker than expected, so we have some time left for questions and answers. First of all, there's a technical question from the audience that I'll postpone. This is about the previous presentation, sorry. Let's go on with this. First of all, did you implement your algorithm in Maple? And if so, is it available for download?
We do this, as will be available in the sometimes. It's now is it is free. It is needed download for download in some time.
It's not yet available for download.
Or contact to me.
I'm not sure if we got that. You said it's not yet available for download?
Вот если такая, ну, наша еще трехмерная, ну, многомерная еще не вышла. It is not programmed in the final version of the program, but some prototypes. It's for contact to me, or at our last version will be put of the Joint Institute of Nuclear Research program library. Generally.
Yeah, that's good to know. Thank you. The next question is about error estimation. Typically in interpolation formula, you have an error analysis with involving the next order derivative and divided by a factorial and so on. In the one-dimensional case, it's very simple, but what about interpolation error in your two- and three-dimensional approach? Did you do some error analysis here?
Yes, this analysis is possible. For example, to calculate of the different grids of the different polynomials. So it's a Ronke coefficient. So it's остаточный шлем как.
Okay, perhaps an add-on question. Does your Maple procedure output these error estimates?
Yes. Yes, it's
okay. Yeah, could not hear everything due to the low phone quality. The audio quality was not very good, but we got there.
For example,
yes, that's good to know.
Estimation is for the eigenvalues is the constant times the step over 2p. P is the order. This estimation can be calculated by Runge or calculate, or give the linear discrepancy in the double log scale versus the energy.
Okay, yeah. So there seem to be no more questions on this talk. So thank you again for your presentation. And since one of the 4 speakers did not show up today, it's Yuri Demjanovic of St. Petersburg State University. We have some time left in this session for general questions, and you're still free to type them into the Q&A panel. And we have one already about the talk by Alexandre Trocado. And the question is about the file format. Your slide, it says, your slides are stored in a file of type key. I'm not able to open this kind of file. Is it possible to get your slides as another file type, for instance, PDF?
Not difficult. Not difficult. I will give our slide. We can share our slide. It's a presentation from Apple Keynote. I think I understand the question.
Yeah, it's not about the worksheet. It's about the presentation slides. The attendant is asking, can you provide them as PDF files instead of key files?
Okay. It just convert the Keynote to PDF file.
Okay. Sounds good.
Okay.
Thank you very much. There's still some time left for general questions to all 3 presenters. Since everything seems to be covered right now, let's thank all speakers again for their presentations today. And on behalf of MapleSoft, I would like to thank all attendants, all contributors for joining us this year to the Maple conference. I think it was a successful show. We had more than 400 active registrants online, and we had 54 contributed sessions, 2 keynotes, 3 keynotes altogether, an art gallery and a prize competition. And I think it was a rich show, entertaining, and with lots of content. Even today in the Maple in Mathematics session, there was a clear emphasis on algorithms, which we appreciate, and we hope that the contributions are valuable to all attendants. Thanks again, and let me encourage you for some consideration. For instance, if you want to contribute, there are various ways. Let me note the Maple Transactions, the online journal that has gone online last year. You can also submit your applications to the Maple Cloud. You can post on Maple Primes, or you can visit the newly designed Maple Application Center. Its design is currently in a beta phase, which makes things more accessible and easier to search. And we hope you will enjoy the design. And of course, we will always appreciate your feedback on all those platforms. Okay, with that, thanks again for joining us this year. And this is the last session today. I think we have no further events, so this will actually close the session. Hope to see you next year and enjoy your work with Maple.
Is the sessions will be also available as recordings?
Yes, everything will be online via the main conference website for at least 1 year.
Ah, okay.
So there's no time pressure. And if you enjoy watching the remaining videos, I myself have not yet even seen all of them. That's still possible without any pressure. Enjoy.
Okay, that's great.
Yeah,
That's great.
to be clear, the recorded presentations are available now. The sessions, the Q&A sessions and the keynotes that were live will maybe take us a couple weeks to process and get posted, but they will be in that conference platform for the next foreseeable future.
Okay, great. Thank you very much.
You're welcome.